is greedy algorithm, a simple intuitive algorithm that is used in optimization problems. The algorithm makes the optimal choice at each step as it attempts to find the overall optimal way to solve the entire problem. Greedy algorithms are quite successful in some problems, such as Huffman encoding, which is used to compress data, or Dijkstra's algorithm, which is used to find the shortest path through a graph. History of greedy algorithms. Here is an important landmark of greedy algorithms. Greedy algorithms were conceptualized for many graph walk algorithms in the 1950s. Ger Dijkstra conceptualized the algorithm to generate minimal spanning trees. He aimed to shorten the span of routes within the Dutch capital, Amsterdam. In the same decades, Prim and Kruskal achieved optimization strategies that were based on minimizing path costs along weight routes. In the 70s, American researchers Corman, Rivest, and Stein proposed a recursive substructuring of greedy solution in their Classical Introduction to Algorithms book. The greedy search parad was registered as a different type of optimization strategy in the NIST records in 2005. Till date, protocols that run the web, such as the Open Shortest Path First (OSPF) and many other network packet switching protocols, use the greedy strategy to minimize time spent on a network.
Greedy algorithms, pros and cons. Pros: simple, easy to implement, and run fast. Cons: very often they don't provide a globally optimum solution. There is an ordered list of resources with cost or value attributions. These quantity constraints on a system you will take the maximum quantity of resources in the time a constraint applies. For example, in an activity scheduling problem, the resources costs are in hours and activities need to be performed in a serial order.
With this example, we'll see how the algorithm makes locally optimal choices, however, ending up at a non-optimal solution. In this tree, we are required to get the largest root to leave sum. That is, starting from the upper node, which is 3, we have to find a path ending at a leaf node and having sum of nodes as maximum. Let's start. The sum at start is 3. There are two possible paths, 4 and 7. However, here, we make a greedy choice and choose the one that maximum, which is 7. Our total now is 10. Now we have to choose between 9 and 11. A greedy choice would be select the larger of the two. We select 11 and end up having a path with sum as 21. Now we will try another path. If we start from 3, go to 4, and then 20, this path would give us a sum of 27, which is greater than the one we have achieved through greedy method. So here we conclude that making locally optimal greedy choices don't always give us globally optimal value.
When are we supposed to use the greedy method? All problems which are generally solved using greedy algorithm satisfy two properties. Number 1, the greedy choice property, making the best choice at the moment leading to a global optimum. Next property is the optimal substructure. Properties whose optimal solution can be constructed efficiently from optimal solutions of its sub-problems. This property may look similar to dynamic programming, however, one thing to note here is that greedy algorithm never reconsider its choices.
Greedy strategies and decisions logic, in its AC ways form, was boiled down to greedy or not greedy. These statements were defined by the approach taken to advance in each algorithm stage. For example, Dijkstra's algorithm utilized a stepwise, greedy strategy identifying hosts on the internet by calculating a cost function. The value returned by the cost function determined whether the next path is greedy or non-greedy. In short, an algorithm ceases to be greedy if at any stage it takes a step that is not locally greedy. The greedy problems halt with no further scope of greed.
Applications that use greedy algorithm.
Dijkstra's algorithm. Dijkstra's algorithm is used to find the shortest path between nodes in a graph. The algorithm maintains a set of unvisited nodes and calculates a tentative distance from a given node to another. If the algorithm finds a shorter way to get to the given node, the path is updated to reflect the shortest distance. This problem has satisfactory optimization substructure since if AA is connected to BB and BB is connected to CC, and the path must go through AA and BB to get the destination to CC. Then the shortest path from AA to BB and the shortest path from BB to CC must be a part of the shortest path from AA to CC. So the optimal answer from the subproblems to contribute to the optimal answer for the total problem. This is because the algorithms keeps track of the shortest path possible to any given node.
Huffman coding. Huffman encoding is another example of an algorithm where a greedy approach is successful. The Huffman algorithm analyzes a message and depending on the frequencies of the characters used in the message, it assigns a variable length encoding for each symbol. A more commonly used symbol will have a shorter encoding, while a rare symbol will have a longer encoding. The Huffman coding algorithm takes in information about the frequencies or probabilities of a particular symbol occurring. It begins to build the prefix tree from the bottom up, starting with the two least probable symbols in the list. It takes those symbols and forms a subtree containing them, and then removes the individual symbols from the list. The algorithm sums the probabilities of elements in a subtree and adds the subtree in its probability to the list. Next, the algorithm searches the list and selects the two symbols of subtrees with the smallest probabilities. It uses those to make a new subtree, removes the original subtrees or symbols from the list, and then adds the new subtree in its combined probability to the list. This repeats until there is one tree and all elements have been added. At each subtree, the optimal encoding for each symbol is created and together composes the overall optimal encoding.